Welcome to this M1 video on pulleys. Now, in this section, kind of all of the model of systems that we'll look at will all basically have light inextendable string passing over a smooth pulley. So that means that the tension will be the same on both sides of the pulley. And for the ones we're looking at, the string will either be horizontal or vertical either side of the pulley. Now, when we move on in the next load of videos where we'll start looking at things at angles, then we can look at more complicated systems. But for now, we'll be sticking with just horizontal and vertical kind of hanging pieces of string. Okay. Now, there's nothing really new to add in this section. It's just going to be looking at a different type of question. So I think the easiest way to do that is to look at two examples. Now, what we'll be looking at is examples with questions like this, which contain a pulley, two pieces of string attached to some sort of weights there, and basically, we have tension coming off the pulley, we have tension coming down this way, we have the mass times gravity of both of these objects, whatever mass they may be. They could be, I suppose, two different masses, so call one M, call one capital M. And then sometimes we also have the force of the pulley being attached to, some sort of ceiling or, beam or something like that. Okay, and then depending on which direction of motion it is, they usually start at rest, so they're held in place. And then say that capital M is greater than little m, then we know that this is going to move up this direction and down in this direction. It's going to accelerate that way. Okay, so that's kind of one type of question that we will be looking at. And then the other one will be something like this, where we'll have some sort of box, the rope is attached like that, and then hanging down we'll have something on the bottom there, so that will have its mg, it's tension in the pulley like so, and maybe this might be on a rough kind of surface, and this will be my friction. Okay, my frictional force that way. Okay, so that'll be like mg or capital Mg, and a reactional force there. Okay, so that's kind of like the two styles of questions that we are going to be looking at. Okay, and this is what I mean by, they're either hanging vertically or horizontally. So a vertical one and a horizontal one. Okay, and in all of these cases, the pulleys are a light, smooth pulley. Okay, so it has no mass is negligible. Okay, no friction. It means that the tension is going to be the same either side of the pulley. Okay, but that's the type of questions we're going to be looking at. So let's start. We'll do an example of this type and an example of this type, and then I've got 3 past paper questions for you to have a go at. So here is the first example. Particles P and Q of mass m and 2m are attached to the ends of a light inextensible string. The string passes over a smooth fixed pulley, and that the masses hang with the string is taut. Okay, now this kind of thing I'm going to miss out in the actual questions just to save myself time and space. But, you know, I'm not going to repeatedly write the smooth fixed pulley and light inextendable string. Okay, you can assume that is true for each of the questions we do later on in this video. The system is released from rest. Write down an equation of motion for P and Q. So for part A, let's start off by drawing it. So a little sketch. It's got two masses there. This is going to hang down with mg, and this one's going to hang down with 2mg. And then that's going to be tension in the string, and then tension in the string from the pulley. Okay, so that's initially what's happening. Now, this is P and this one is Q. Q is obviously heavier, so this one's going to accelerate this way, and this one will accelerate this way. And the acceleration will be the same for both. So part one is write down an equation of motion for P. So for P, now we're going to resolve vertically, and we're going to resolve pointing up because that's the direction it's going. And we're using F equals MA. So T is going to take it up, and mg will take it down, and then it's going to be equal to ma, and we don't know what a is. So that is my first equation. Now my second equation is for Q. For this we're going to resolve vertically, but we're going to resolve downwards. So that's going to be 2mg. So again, using F equals ma, minus T equals 2ma. So just to run through what we're doing, with P we had T going up and mg going down. So the resultant force would be T minus mg because we're moving upwards. So that is my F and then ma. For Q, we're moving downwards and we're taking down as positive. So 2mg minus T is the force going down, and that is equal to m times a. And that therefore gives me two equations. Now, obviously in an exam question, it wouldn't necessarily break it down this way. Okay, you might just be, you know, find the value of T or find the value of A, and you'd have to create these equations. Now, B is find the acceleration of each mass. Now, the acceleration of each mass is going to be the same. And what I want to do is I want to eliminate T because that's one of my other unknowns. So if we do 1 plus 2, then that gives me T minus mg plus 2mg minus T equals ma plus 2ma. So the T's are going to cancel. 2mg take away mg is mg equals 3ma. The m's will cancel, so a equals 1/3 g. Okay, so it's 1/3 g, and that is meters per second squared. Now, part C is find the tension in the string. So now we can use our equations. So from 1, we've got T minus mg equals m times 1/3 g. So that's T equals 4/3 mg. Okay, D. Find the force exerted on the pulley by the string. So if I take a look at the pulley again, the pulley is obviously, like this. String on both sides is T, and then this is that force, the opposite force that's exerted. So it is effectively 2T. Okay, so it's 2T, which equals 8/3 mg. I should put newtons in both of these. And that is part D done. Now part E is find the distance moved by Q in the first 5 seconds, assuming that P does not reach the pulley. That little bit at the end is always put in there because P and Q are attached to the same string, if one of them hits the pulley, then obviously it's going to stop moving. So that assumption is always there. So it starts at rest, doesn't it? Acceleration is 1/3 g. T is equal to 5, and S is what we want to find. So S equals ut plus a half at squared. So that's going to be 0 plus half times 1/3 g times 5 squared. And that is 40.83 meters to 2 decimal places there. Okay, nice and straightforward, I believe. And then finally, F, state how you use the fact that the pulley is smooth in your calculations. Well, it's quite simple. The tension in the string is the same at P as at Q. Yep, the tension remains consistent throughout the string, basically. Okay, and that is all there is to it. So that's one where they both are hanging vertically. Let's look at one where one is horizontal and the other one's vertical. So here we have it, two particles A and B of mass 200, 400, connected by light in the center string. Particle A lies on a rough horizontal table from the pulley. B hangs freely with the string taut. So let's look at what we've got here. So I've got a rough horizontal plane, like so. I've got a pulley on the end here that hangs down. This is attached to A, isn't it? And then we have B on the bottom. So that's tension there, tension there. This has a resistive force, doesn't it, of 0.04 G. Does have a reactional force there, and this one is, so A is 200 grams and B is 400 grams, so 0.4 G newtons in terms of the weight. And let's make this one a newton, so 0.2 G newtons there. So that is kind of what we've got. The heavier weight, so we would assume that this is moving in this direction. Okay, so you know the A will move towards the pulley and B would move towards the ground. So that's what is kind of happening. Now let's look at A. So we want the acceleration of the system. So let's have a look at what's happening. So for A, we're going to resolve horizontally. And of course using our F equals ma. So that's t minus 0.04 g, and that's going to be equal to 0.2 a. And then for b, we will resolve vertically, but we'll do it vertically downwards. So 0.4 g minus t is equal to 0.4 a. So let's call this 1 and 2, and we're going to do 1 plus 2. So when I add them, the t's are going to cancel, so we're going to have 0.4. No, that's 0.36, and then 0.6a. I almost added them instead of subtracting the 0.04 g there. Oh, that's g. So a equals 0.6 g meters per second squared. Okay, so that is A done. So the time taken for B to reach the ground, well, we know that it starts off at 0 for speed. S is 0.75. A is 0.6 g, and then T we want to find. So S equals UT plus a half AT squared. So that's 0.75 equals, so that's 0 plus a half times 0.6 g times t squared. So t squared is 0.255 and so on. Square rooting that and obviously taking the positive answer, t is 0.51 seconds, and this is to 2 decimal places. Now we move on to part C, the total distance travelled by A before it comes to rest. So first we need to find the speed of B when it hits the ground. Okay, so we know U is 0, S is 0.75, A is 0.6 g, and we want to find V. So V squared equals U squared plus 2AS is what we're going to use. So that is 0 plus 2 times 0.6 g times 0.75. And square rooting that gives me 2.9698. So it's going to be 3.0 3.0, two significant figures there. Or let's do it to 3 significant figures, 2.97 to 3 significant figures. Okay, but we'll use the full answer in the calculator. So that's the velocity of B, and now the speed that B is going is the same as the speed that A will be going. So basically, once B hits this bottom here, then A will continue sliding across the table and its initial velocity will be B. Okay, but we need to find out what its acceleration will be at that point, because there'll be no force pulling it, so it won't be traveling with this acceleration. Okay, so there'll be no force pulling it, but there will be this resistance force. So it'll actually be decelerating as it slides across the table. So if you imagine it, it's like pushing an object, basically. You know, this A has been tugged by B, and then it stops being tugged. Okay, so then A just continues to slide across the table until it comes to rest. So now VB will be our UA in our final calculation, but until that point we also need to find out what A is going to be. So if you imagine that F equals MA, now there's no forward force, it's just this 0.04 G resistance force, and its mass is 0.2, and A we want to find. So A is minus 0.2 G. So now we can model it. So U is going to be equal to 2.97, and obviously I'll use the full calculation of that. V is 0, A is minus 0.2 G, and S is what we want to find. So we want to use V squared equals U squared plus 2AS. So that's 0, that's 2.97 squared, plus 2 times minus 0.2 G times S. So 0.2 times 2 will be the 0.4. So we've got 0.4 GS equal to the 2.97 squared. So S is equal to, and S is 2.25 meters. So the total distance is, right, it dropped 0.75, didn't it? So it moved 0.75 meters when B was pulling it, and then it did an additional 2.25. So in total, it went 3 meters. And there we have it. That is then the second example. So a little bit more thought, a little bit of using SUVAT in with our F equals MA. And you do have to do that, you know, the object moving freely. So sometimes, you know, with the two vertical ones, you know, when you've got the pulley and you've got two vertical, where this one, say, hits the ground, and then this one carries on going up freely under gravity. And you've got to work out, you know, like how far it's travelled, or how high the maximum height it goes and stuff like that. So there is a mixture of using F equals MA and using SUVAT. So hopefully you found this video useful so far. If you have, you know, don't forget to hit that like button. If you're yet to subscribe, smash the subscribe button now. And if you're willing and able to help me out financially, hit that join button. Otherwise, let's get into the questions. So the questions are quite long, and for me to be able to fit them all in, I've had to take out some bits. So I've taken out that the string is light and inextensible, and all pulleys are smooth, light and fixed in place. Okay, so you can assume that for each of these 3 questions here. So pause the video now to have a go at question 1. Welcome back. Pause the video now to have a go at question 2. Welcome back. And pause the video now to have a go at question 3. Welcome back. So hopefully you've had a go at all three questions there. They were past paper questions, just adapted slightly. Now let's have a look at the answers. So we have two particles P and Q of masses km and 3m. So P has km g going down and Q is 3m g going down, and k is less than 3, so the acceleration is going to be in this direction. Okay, so the system is currently held at rest where the string is taut. Don't forget our tensions, they're all going to be equal, and they're held at the same height. System is released. After release, Q descends with an acceleration of 1/3 g. Calculate the tension in the string. So for A, we're looking at for Q. So it's F equals ma, and then that's 3mg minus T equals, and then the mass is 3m, and the acceleration is 1/3 g. So the 3m and the third is going to give me 1 mg. So 3mg minus mg equals T. So T is equal to 2 mg newtons. Now, part B. Now we'll look at P. So this one, Q we were resolving down, P we are resolving upwards. F equals ma, so that's T minus kmg, and that's km times 1/3 g. Oh, and T is 2 mg, isn't it? 2 mg. So we've got m's throughout, so we can cancel the m's. We've got g's throughout, so cancel the g's. So we've got 2 minus k equals 1/3 k. So 2 equals 4/3 k. So k equals 3/2 or 1.5. And that was, what we had to show, and we've done that. So let's move on to the next part. So after descending for 1.8 seconds, the particle P reaches the plane. It is immediately brought to rest by the impact of the plane, and the initial distance between P and the pulley is such that in subsequent motion, P does not reach the pulley. So what is happening here is, if I've got this Q here has hit the bottom and stops. Now P then keeps on moving freely under gravity without hitting this pulley. So after 1.8 seconds, the force stops and then P continues to go. So what we've got to do is find out how far, P rose up from its original position. So in that 1.8 seconds, and then how far under gravity it continues to go. So I'll just get rid of this, and let's start off with the 1.8 seconds first of all. So they start off at u equals 0, travel for 1.8 seconds. The acceleration is 1/3 g, and we want to find s. So s equals ut plus 1/2 at squared. So So it equals 0 plus a half times 1/3 g times 1.8 squared. And that is 5.292 meters. Now, we also need the speed, its final velocity at this point, because that's going to be the initial velocity when the system changes. So we need V. So V equals U plus AT. So U is 0 plus 1/3 g times 1.8, which is 5.88 meters per second. So now for phase 2, this is now moving freely under gravity stage. So at this stage, U is 5.88. Acceleration is g. So if we take it upwards as positive, the g is going to be a deceleration. We want to find, v is going to be 0, because the maximum height, the velocity will come to 0, and we want this distance here. So v squared equals u squared plus 2as is what we're looking at. So that is 0, and it's 5.88 squared plus 2 times minus g times s. So 2gs equals that 5.88 squared. So s is 1.764 meters. So total distance is 2 of these and 1 of these. Because if you think the 2 items started this distance s above the ground, then this travelled a further distance s above the ground, and then it did this under free movement at the top. Okay, so if I call that S2 and these two as S1, so what we need is 5.292 times 2 plus 1.764, and that will give me the total distance above the ground. And that is 12.348. Now I've just realised it's in terms of g, so I can take this, divide by 9.8, so it equals 1.26 g. So divided by the 9.8. And what I could have done is left them in terms of g over here. So there's 5.292 divided by 9.8 is 0.54 g, and this one is 0.18 g, like so. So it should have been, 0.54 g times 2 plus 0.18 g. So 0.54 times 2 plus 0.18 gives me the 1.26 g there. Okay, so just a little small error on my part in terms of I forgot to read the question, okay, because it's in terms of g, and I did it just in full decimals, but it's easily solved at the end. Just divide by your 9.8, okay, to get the answer. So hopefully that made sense, and hopefully the double this distance made sense, because as this drops, this increases but we want the total height in meters above the plane. So it's double this distance plus the moving bit when it's moving freely under gravity. Okay, so hopefully you got that question out there. If you didn't, hopefully now you understand it and it makes sense. Now let's have a look at question 2. So we have these. The mass of A is mg and the mass of B is 3g. That's the tension in the string. And we've got M is greater than the 3g, so it's going to move in this direction. Okay. The release from rest after A has been descending for 1.25 seconds, it strikes the ground, and it strikes the ground before particle B reaches the pulley, standard thing there. So for A now, show that the acceleration of B is 3.2 meters per second. So the acceleration of A is equal to the acceleration. My spelling is terrible when I'm speaking. Okay, so acceleration of A is equal to acceleration of B. So we can look at A there. So taken down as positive, U equals 0, S equals 2.5 meters, T equals 1.25 seconds, and A we want to find. So that's S equals UT plus a half AT squared. So 2.5 equals, so that's 0 plus a half times A times 1.25 squared. And if we rearrange this, A equals 3.2 meters per second. Okay, so now we're on to B. Find the tension in the string as A descends. So, as A descends, so we need to look at B because we don't know the mass of A. So B we're going to resolve vertically upwards, and F equals MA. So that's T minus 3G equals 3 times 3.2. So 3.2 times 3 is going to be 9.6 plus the 3G is going to give me that T is 39 newtons. So that is T. Now show that M is 65 over 11. So now we can go to A. So for A, and we're going to resolve vertically downwards because that's its motion. So F equals MA. The force will be mg minus T is equal to M times 3.2. And T is 39, isn't it? So I can rub that out and put 39 in there. Right, so take the 39 to the right, and then we've got 9.8g take away 3.2g. So that's going to be 9.8 m take away 3.2 m. So 6.6 m. And 39 divided by that is 65 over 11 as required. Okay, and that is question 2 done. I think question 2 was actually quite a bit easier than question 1. Let me know what you think in the comments. But otherwise, let's get into question 3. Oh no, I forgot about the later part of question 2. So, when A strikes the ground, it does not rebound and the string becomes slack. The particle B then moves freely under gravity without reaching the pulley until the string becomes taut again. Find the time between the instant when A strikes the ground and the instant where the string becomes taut. So we've gone from this where A is striking the ground. So A now has struck the ground, and then the string becomes slack and particle B continues moving up this way and freely under gravity. Okay, and then we want the time between the instant A strikes the ground and the instant the string becomes taut again. So what we're looking at is that time that it goes to the top and then comes back to this point, and then the string will be taut again. So the time that this moves up till it's V equals 0, we want that time, and then for it to come back down to this point where the string then will become taut. So we'll find the time between this point and the point it reaching its maximum height, and then the time dropping back down will be the same, so we'll double the time in the end. So let me just get rid of this so I have room. In fact, let's get rid of this as well, so I have plenty of room. So we're looking at part D. So we've got to work out the speed at which particle A strikes the ground. So it started off at 0. We want to find what V is. A was 3.2. S was 2.5, wasn't it? So V squared equals U squared plus 2AS. We also had the time, so we could use that as well. But anyway, 0 plus 2 times 3.2 times 2.5. We'll find out. So V is 4 meters per second. So that is now under gravity. So for B, freely under gravity. Actually, let's move that up there. We've got U is 4, V is going to be 0. We want the time, and A is going to be gravity, so take it upwards as positive because that's the direction it was moving. So we want something with V, U, A and T, so V equals U plus AT. So 0 equals 4 plus minus GT. So GT equals 4, so T equals 4 divided by 9.8. I'll leave it as a fraction, 20 over 49 seconds. Therefore, total time is 2t, which I explained earlier. So 40 over 49 seconds, or what's that as a decimal? 0.816 to 3 significant figures. Now, question 2's done. So let me know in the comments if it's still the easiest one. Maybe, maybe not. This part D did make it a little bit harder. Now let's have a look at question 3. Okay, number 3, we've got a box P 2.5. It's on a rough horizontal plane. Pulley, sphere of 1.5 kilograms hanging there. The magnitude of the frictional force is K newtons. System is released from rest. After release, Q descends a distance of 0.8 meters in 0.75 seconds. So let's kind of put all of our values onto this diagram. So this has got a frictional force of K newtons. We've got the tension in the string, and this is 1.5 G newtons going down. Okay, I think that's everything. So I can get rid of that little bit and give myself a little bit more room. After release, Q descends a distance of 0.8 meters in 0.75 seconds. Modeling P and Q as a particle. Work out the acceleration of Q. So for Q, we'll take downwards as positive. They're going to start at rest. It's going to travel a distance of 0.8 meters. Time is going to be 0.75, and A is what we're going to try and find. So S equals ut plus half AT squared. So 0.8 equals 0 plus a half A times 0.5 squared. So rearranging this, A is 128 over 45, which is 2.84 meters per second squared to 3 significant figures. And I'll store that in my calculator in case I need it later on. So next we need to find the value of K. No, sorry, before the value of K, show the tension in the rope is 10.4 newtons. So we'll stick with Q, and we're going to resolve downwards. So F equals ma, and I know the acceleration is going that way. Okay, so that's 1.5 G minus T equals 1.5 times that 2.84. Of course, I'm going to use the full value in the calculator. Now rearranging, and that gives me that T is 313 over 30, which is 10.43, recurrent to be exact, but 10.4 newtons to 3 significant figures. So that is part 2. Now part 3 is find K. So now we can look at P, can't we? And we can resolve horizontally. So F equals ma, and we've got T minus that K is equal to 2.5 times the 2.84, and of course T we've got as our 10.4 newtons, haven't we? So again, I'll use all the full values in the calculators just to be aware, you know, like I store this as B, I stored this as A. I often, when I'm doing my calculations, I make little notes like that alongside where I've saved them. So the 10.4 is at B, and then I will subtract 2.5 times A, my acceleration, and that gives me that K is 299 over 90, or 3.8 0.32 to 3 significant figures, and of course that's newtons. Okay, so that's all there is to that bit. Now we've just got left part B. State how in your calculations you have used the information that the string is extensible. The tensions in all parts of the string are the same. So part B, the tension in all parts of the string are the same. And that is question 3 done. That was actually the easiest one, definitely. Okay, so hopefully you enjoyed this video. This is the end of chapter 4 if you're following the Edexcel textbook. The next bit we go on to is forces and friction, and we start looking at forces at different angles and resolving them. And now we're getting really into the more mechanics maths that you should get very familiar with. Okay, so hopefully you found this video useful. Hit the like button if you did. Comment down below with any difficulties you had, or some of those questions. And yeah, I'll see you in the next video.